Hello and welcome back. Today we're going to talk about Bevy Prototype Lyon as we said we were going to do before. Now, Bevy Prototype Lyon has a decent amount of code in it, so I'm going to split this up into multiple videos. If you're unfamiliar with Bevy Prototype Lyon, I'll link the first video in this series in the description, but otherwise it's a 2D and SVG rendering library for Bevy, or rather, it's a Bevy plugin that's powered by a separate crate called Lyon that handles all the tessellation and stuff. And we're working our way down from usage of the Bevy plugin into the internals of the Bevy plugin into the WGPU based examples for the actual Lyon crate. So today specifically, I wanted to cover the render pipeline because render pipelines in Bevy are a super interesting topic. You can see that we are in the Bevy Prototype Lyon repo in source render mod.rs. I'll just quickly show that there are a couple of Rust files here. Inside of the render folder, there is a shape.wgsl and a mod.rs. We're in the mod.rs. And this defines the render pipeline for actually rendering 2D shapes to the screen. Now, there are a set of files that are dedicated to setting up and handling fills and strokes and things like that. But today, all we're looking at is how to set up the render pipeline, which will be the shaders, the bind groups, the bind group layouts, and things like that, to make sure that our vertices and things like that all get passed through correctly and rendered by Bevy in WGPU at the end of the day. So we've got a whole bunch of Bevy items in scope here. This shape is super important. It is a marker component, so it doesn't contain any data, but it's a component that we can attach to entities in the regular Bevy world. So there's two Bevy worlds that we care about today. There's the regular game world, which is if you write a system query for some resources or some entities or something like that, that's the world that you're working in. And then there's the render world, which is completely separate. So this component here, this shape component, defines for us which components we should be able to pull out from the regular world into the render world so that we have our data available. I think the render pipeline that we're using, so we define shape pipeline here, which is the custom pipeline in Bevy's terms. I think it's super interesting that we use basically the Mesh 2D pipeline. So it's just wrapping over the regular 2D mesh renderer that Bevy already has. And we do this by creating a field that says some arbitrary label. So we called it Mesh 2D pipeline because that makes sense. And we set it equal to Mesh 2D pipeline, which comes from the Bevy resources above, specifically from Sprite. So Mesh 2D pipeline comes from Bevy Sprite. We implement from world, which if you're familiar with Bevy, you'll know that from world is basically the same as implementing the default trait, except for the fact that we have access to the world. So in this case, we can create a Mesh 2D pipeline from just a regular world and we pass the world in and we have one. So wrapping the Mesh 2D pipeline is really nice because we don't have to rewrite all of that logic to set up our pipeline here. We then have to implement specialized render pipeline for the shape pipeline. Remember, shape pipeline is our custom render pipeline, and this sets some of the features of our pipeline. So by defining this specialized function, we'll return a render pipeline descriptor, which if you went through the Learn WGPU series, this will look very familiar to you. If you haven't, that series is available. I'll link that in the description as well. So we use the Mesh 2D pipeline key type because we're basically extending a Mesh 2D pipeline. We specialize the layout of the vertices in our vertex buffer. So in this case, so again, if you went through the Learn WGPU series, you will have seen this float 32 by 3, float 32 by 4 type or approach to defining the way that our buffer is set up and the way that the data sits inside of it. This is doing the exact same thing. It's saying we basically have a vec3 of F32s and a vec4 of F32s laid out right next to each other. And that defines one vertex or one vertex attribute, which makes sense if you look at the vertex layout that we create next. So vertex buffer layout, this is the layout of the vertex buffer, has this function called from vertex formats. And we specify the vertex step mode. So this is when we step over the data to the next one. How far do we go? In this case, we're stepping from vertex to vertex. And then we pass in our format. So we have got a vec3 of F32s and a vec4 of F32s. So we've got effectively 7 F32s in a row. Then we return our render pipeline descriptor, and this will look very familiar as well if you've gone through the Learn WGPU tutorial series. We set up a vertex state using the shape shader handle. So if we scroll back up, or maybe it's not up. Maybe I'm mistaken. Yeah, there we go. Okay, so it's down. If you scroll down, you'll find pub const shape shader handle. And this is a handle, so that's the Bevy type handle to a shader. And there is a Bevy plugin here, like overarching, to set all of this stuff up for us. So when our Bevy plugin gets initialized, we get the shader asset database and we set our shader, shape.wgsl, which is in the same folder, as a shader inside of that. So that's how we get that handle. And this handle is just a specific ID that is unique to us. So it's basically arbitrary. We could choose anything we wanted here. So that's how we get that ID here. We set it as a const ahead of time to be some constant value that we made up. And we use that for both the vertex shader and the fragment shader. We set up the entry points as vertex and fragment respectively. We don't set any shader defs. And then we set up the vertex layout for the buffer. So we only have one vertex buffer here, which you can tell because we have the vertex layout, which specifies the format for one buffer. The fragment shader now has a color target state, which should also look familiar if you've gone through the Learn WGPU series. Bevy has its own default texture format. So it has one that it prefers. So we grab the Bevy default instead of just like any arbitrary texture format. We set the blend mode to alpha blending, and we specify a value for right mask. Next, we need to set the layout for our uniforms. So in this case, we're reusing the Mesh 2D pipeline, remember? So we've got the layout for the view information and the layout for the mesh information. And we're just pulling from the Mesh 2D pipeline, so it's not super interesting. But it is interesting that we can kind of extend this pipeline like we're doing. We also set the primitives. So these are things like, should we call the back faces and stuff like that? We don't have a depth stencil, but we do set up multi-sample anti-aliasing. And finally, we give it a label because if we look at anything inside of debugging software like RenderDoc, we want everything to have nice names. So just to repeat, this is the implementation of specialized render pipeline for this shape pipeline that is controlling how we render these 2D shapes that we've defined. This type is something that confused me when I first looked at it. It is setting up a draw call using just types and const generics. So Bevy will understand this, and it will say, set the mesh 2D view bind group to bind group 0, and set the mesh 2D bind group itself. So there's mesh 2D view and mesh 2D to bind group number 1. And it does this using const generics here. And this is basically our draw call. So it's defining how we actually want to render when we want to render. Then again, we touched on this a little bit earlier, but there is an actual just regular Bevy plugin set up here. So we implement plugin for the render shape plugin. We set up our shaders like we talked about earlier. And then if you've seen the shader videos or some of the more advanced shader videos that I've done, this might look familiar to you. Because the render world is a separate world, we have to get the render app or the sub app that is the render world. And then instead of doing app.init resource or something like that, we do render app.init resource. So we add our render command, which adds to the transparent 2D phase, and draw shape is our render command. So if we look at the add render command function, it takes two type arguments. One is called P and one is called C. If we look at the where clause, we can see that P needs to be a phase item. So it's the phase of the render. If we click on phase item, it'll tell us a little bit more. So an item which will be drawn to the screen, a phase item should be queued up for rendering during render stage queue. Afterwards, it will be sorted and rendered automatically in render stage phase sort and render stage render respectively. And then C is going to be our render command. Our render command runs an ECS query and produces tracked render passes. We haven't talked too much about render passes, but suffice it to say, tracked render passes are a Bevy concept for tracking to make sure that the render passes that we set up are valid and can be run. So after setting up our render command saying that we want to draw shape, which is the type we defined earlier, in the transparent 2D phase, we initialize our shape pipeline, which we defined earlier. We initialize the specialized render pipeline's shape pipeline type. So we have our shape pipeline struct resource that has a from world implementation and gets constructed for us. And then we also construct the specialized render pipeline for the shape pipeline, which we've also implemented. And then we have two systems. We have extract shape added to the extract render stage and queue shape added to the queue render stage. Extract is fairly understandable. The extract function exists to take things from the regular Bevy app world and bring them into the render world. So we query for commands the previous length. So if you've never seen local here, this is a local stateful variable that we can update. It's local to this query, or rather local to this system. Our query uses extract to query for any entities that have shape. So this is our marker component. So we can pull things from the render world. We set up a new mutable variable called values. That is a vec with the previous length capacity. So in general, what this was going to end up being is all of the shapes that we are supposed to be rendering. We loop over the entire query for the entity and the computed visibility. The computed visibility is here so that we can not render things that aren't visible, so we can save some work. But otherwise, if it's visible, we push the entity in with the shape component. We set our local variable here, our usize, to the length of this vec, and then we insert or spawn batch for all of those values. So insert or spawn batch is an interesting function on commands, which for a given batch of entity bundle pairs, it'll either spawn the entity with the bundle that we give it, if it doesn't exist, or it'll insert the bundle onto that entity if that entity does exist. And the reason for this is that it is faster than doing the equivalent operations one by one. So that's what this is doing. It's taking the entity and then the components or the bundle. In this case, it's a tuple. So the reason that we have this comma here is that if we just had the parentheses around it, it would be parentheses around a value. But because we have that comma here, it is a tuple of two elements where the first one is shape. So it's a tuple of one element, basically, which has bundle implemented for it. So tuples have bundle implemented. So that's how we extract all of the shapes that we want to render. And then we have to queue them all up so that we can actually render them. So we define this queueShape function, which pulls in quite a few types or values that you might not have seen before. We grab all the draw functions for the transparent 2D phase as resources. We grab our shape pipeline, which is a resource in the system. We grab all of the pipelines that are related to the shape pipeline, so the specialized render pipelines, as mutable resources. We grab the pipeline cache, which is kind of like an optimization, and then a couple other things that we need for the Mesh 2D to work. So shape specifically is a query for Mesh 2D handles and Mesh 2D uniforms that have the shape component attached. If the shape is empty, then we do nothing. We don't render it. If we have an empty shape, we shouldn't render anything. And then for every view, so for every camera that can see some shapes, we iterate to see what the visible entities are. And then we also get this render phase for the transparent 2D phase. So we get the visible entities here and the transparent phase. We can grab the ID for the draw shape draw call that we specified earlier by using the transparent draw functions and the get ID with the draw shape type. So we have the draw shape ID here. We let the Mesh 2D pipeline key get created from its own constructors. So we get the key here. And all we have to do is pass in the multi-sample anti-aliasing samples. Since we're doing work for each camera or each view, for all of the visible entities that exist for that camera, we have to queue all of those entities. So shape, remember, is a query for all of our shapes. We try to get the visible entity if it's a shape. If it is a shape and we have one, then we continue. If not, then we don't do anything. There's nothing down here. So only if the visible entity is a shape do we do something. We grab the render mesh, getting, of course, some help from the Mesh 2D pipeline, which already has some of this stuff set up. And then we call pipelines.specialize with the cache, the shape pipeline, and the key to get our pipeline ID. And finally, in the transparent phase, so the render phase for the transparent 2D, we have to add a transparent 2D with our draw function, draw shape. So this is the ID of our draw call, the entity we want to render, the pipeline used to render it, and then we also specify a sort key so that we get, because this is 2D, the items are going to be sorted according to the Z value from back to front. And because we looked at it earlier, or because we talked about it earlier, we do have a shape.wgsl for actually rendering these vertex buffers that we're giving to it. And you can see here that we have in group 1, the mesh bindings, which we set up earlier, which were set up for us by the Mesh 2D pipeline. Or rather, we used the definitions the Mesh 2D pipeline had to set these up for our own pipeline. The vertex we get, so we're going to do a vertex shader here. And the vertex we get gets a position, which remember is a vec3 of F32s and a color of vec4 of F32s. So now it should start clicking a little bit what these locations actually are. So they're positions in the vertex buffer in this case, which gives us the position as the first vec3 and the color as the second vec4. The actual vertex shader itself is not super complicated. We get the clip position using the fairly typical view projection times the model times the actual vertex position that we're going to render. We grab the vertex color because, again, these are 2D meshes that are generated from SVGs. So we probably have a vertex color for each of the shapes that we're going to render. And then we have the fragment shader also in this exact same file. The fragment shader is even simpler than the vertex shader. We specify the entry point as fragment, and we return the interpolated vertex color. So the fragment will be potentially somewhere between two vertices, right? And this, because we're passing through the vertex colors for all of the vertex positions, the point between them will be an interpolated color between those 2 points. So that's it. That's render pipelines in the context of 2D SVG rendering inside of the context of Bevy prototype Lyon. There's more to go over, but I figured this was big enough for one video, so I'm going to leave it at that. And if you have any questions, put them below, and I'll catch you in the next video.